Hello friends, today topic is brain tumor segmentation and classification. I'm going to use 3D dataset in this experiment, and I hope you guys already heard about LinkNet dataset. This is the dataset structure Brats 2020, and I'm going to show you step by steps how you can create a model for 3D brain tumor classification and segmentation and classification. So let's move forward, and I will use segmentation model of TensorFlow and simultaneously the LinkNet. So here I'm importing the basic libraries of TensorFlow. Okay, this is a lengthy tutorial, so keep watching so that you guys will capable to do the implementation for the same in future. Okay, let me add the title first. Heading. Okay, brain tumor segmentation classification. See, TensorFlow segmentation models of transfer learning. Okay, let's move forward. So import some basic library like TensorFlow, NumPy, Pandas, Matplot, Lip. Don't import twice. sklearn for split, Keras for backend, and blah blah blah. So everything here. Okay, important. One of the library which is important is Nibble, which actually handle the 3D data in NIZ format. Okay, so if you face any error here, that means you haven't installed that library. Whatever the error you face, just type like this in notebook pip3 install xxx, and then that thing will install. Then reload the notebook and start again. Okay, so I have already created this notebook, so I'm going to use step by step process, and so that you guys can understand it better. Okay, this is Brats dataset. This is the path of Brats dataset which is available here. MCCI, lots of images are there, and every image is NIZ format. There are in Brats dataset you can see five images. One is target, definitely the segmented one, and other one are the type of scans MRI images. Okay, then move then os dot path. Okay, then walk through the path, go run. Once you walk through the path, okay, if in the P any map survival data set is available, then remove it, otherwise let it be like that. Okay, this method is for the pre-processing, where we are actually giving the path for modality directory and loading each modality, and thereafter nib load the modality, convert into numpy array, then all the files will get appended in all modalities. Then nifty file from that added a fine, and thereafter you get all files after being pre-processed. So let's add this method here, then move. Okay, let's load some images. Okay, so once you walk through the path which contain the image, each directory contains some subdirectory. In subdirectory there are files, extension, flare, t1, t1 ties, t2, and segmentation. Okay, then from from the first band, okay, pass those files into modality directory. Here you will get only the file path, and then these file path will process to the data pre-processing, and you will get the data at the end. It takes a couple of minutes, just wait. Okay, done. Let's move further. So when you're done with the data pre-processing, okay, it's time to reach out to that point where we are actually concatenating the data, okay, for training and classification, for segmentation and classification purpose. Let's run, then call this function. Okay, so here you can see each files will get appended automatically. So once you have pre-processed and concatenated data, okay, in one dimensional I'm going to use only one type of image, that is T1, and the fourth band consider segmentation image. Okay, so I'm taking that only. So now we have training images and training target. Okay, now it's time to split the data in train and test set. So TRL is train image, TRL is target, 15% data I'm using for testing, and rest of the data for training purpose. It's pretty simple actually. Done. Now for using the segmentation model, it might possible that you need to reshape it the way this already pre-trained segmentation model actually work. Originally these images size, these image having size of 240, but in some segmentation model they takes image of size 224 and some takes 240. So that depends the type of model you are going to you will use. So I'm reshaping it, and after reshaping, passing it to train and X train and Y train for the training purpose. The same we require to do for the validation one. So let's do this thing, this also. So here we get the validation reshape, converting all list into numpy array so that it can pass to the deep learning model. Now it's time to expand the images on the dimensional wise. So numpy expanded. So there are some computational function like dice coefficient, precision, sensitivity, specificity, all if you want to calculate, okay, for computing. So these are the custom functions. Just copy and paste. Let's load some segmentation model. Okay, framework on the backend is Tensorflow Keras, and we have multiple backbones available inside the segmentation model. I'm going to use LinkNet in this tutorial. You can also use Unet, PSPNet, and FPN, future pyramid network, alongside. Okay. So for training purpose, my favorite machine learning model is ResNet. So I'm ResNet 50, so I'm going to use it. Okay. This ResNet on this LinkNet model work as an encoder, and so I'm creating. You can use multiple models here, like this way. Pass ResNet 18 to ResNet, all the pre-trained weights available in the model, segmentation model, act as an encoder so that you can do the data validations and comparison which model is performing which way. Okay, So I'm going to use LinkNet and only the testnet. Let me show you the output in two models. Okay, so let me use some small models, ResNet 18 and ResNet 34 instead of ResNet 50. Okay, because so that both model get trained quick. Okay, once you have the model, okay, all models, then you need then I have used for loop. It takes first model, backbone link, importing the LinkNet. Backbone is I, which is the model. That means whether ResNet 18, 13, 34, 50, mobile net, efficient net, whatever the model you would like to use. Input shape is 224 by 3. That means basically those pre-trained models only takes input shape 3-dimensional. Okay, but in our case the input shape is 1-dimensional. So first what we will do, we will take that input shape, apply a convolutional 2D map and convert that in one channel into 3 channel here. Okay, this is the important step for using the pre-trained weight, and then add the base model onto our process data, and then this output will act as output for a model while compiling, and input is our images. Okay, loss can be atom or anything you can use. Okay, there are metrics available. So built-in loss I'm using binary cross entropy, and there are further metrics: binary accuracy, dice coefficient, precision, recall, sensitivity, so that you can draw the plot for them. So let's run these models. Okay, for the simplicity I'm running this model for 5 epoch, batch size is 8, validation split is during the time of training of extrained data, validation split is here 20. I'm going to use 15. That means 70% data for training, 15% data for validation, and 15% which is we have already split on the top is for testing purpose. So let's make it 15 for validation. Number of epoch I'm going to use less for now. Initial epoch is 0, and I'm going to use 3 epochs, and let's see in 3 epochs how model will performs. It takes couple of seconds, so wait guys. Guys, we provide services all across the globe for thesis. Hope you can find other tutorial in our channel, and if you are pursuing PhD and master thesis, just feel free to contact us. We are here to help you out. Here pre-trained weights are actually downloading for ResNet 18. Okay, takes 1 minute. Once this weight is being downloaded, the training will start. Okay, here it goes. So this is the shape of our LinkNet, and the encoder is ResNet 18. You can see in the very initial epoch the accuracy is 97%, loss is 0.14, because we are using pre-trained weights, so it don't need to get to train explicitly. Only the decoder version required to map the encoding part, so it's really simple to do. Then okay, ResNet 18 comes ends in 3 epochs, and ResNet 34 will initialize, and all these performance will automatically stored in history, and model performance being appended. Okay guys, so let me copy another block. So these are some custom function actually built for comparison of training and training accuracy of different type of model, training, loss, parameters. It takes history and model name, okay, and then grab those model name inside, take as an input and plot the corresponding graphs. So let me let I think training, yeah, training is completed. Let's see how the model is performing. Okay, so you can see here train and validation accuracy. Okay, validation accuracy or explicit is good. Training accuracy boost from the first epoch. In case of dice coefficient of ResNet 18, this is the performance. In case of loss in ResNet 18, the performance. The same we can see here for ResNet 34. Let's move forward and save the model. Okay, I'm not saving it for now because my model is already trained. Let's evaluate for on test data. I have used a small size of data. You can use entire Brat 2020 data for the validation purpose. So you can see the validation parameter. Loss is for ResNet 18, loss final testing loss is 0.7, accuracy is 98%, dice coefficient is 0.22. Okay, precision is high. There is something wrong with precision, I don't know. Sensitivity is 0.32 and specificity is 100%. So let's create some visualization and how the image will look like. Let me run it, this block. So here again the data is appending. So VTR is not, actually didn't use that one in this tutorial. So I'm commenting this part. Yeah, TRL. Okay. So let's see one image and then see other images. Okay, so this is the image of training sequence look like. Brain tumor 3D image in 2-dimensional array. Okay, so okay, so let's plot some sample of both the models. TR consists of all images. We are expanding it. Take all model, print the model name, then each model will do the prediction on the data set. This is the predicted tumor. The the original tumor, predicted tumor, and the original label, how it look like. So I have used a few samples here that how these images will look like. Let's run. It takes couple of seconds actually. Here you can see here ResNet 1, sample 1 for ResNet 18, sample 5 for ResNet 18, and these are the sample for ResNet 34. So let's zoom. So you guys can see the both ResNet pre-trained model are performing good. Okay, the red portion is the predicted one, yellow portion is the original size of tumor, and this is the image where it is actually located. You can see here in every cases the prediction is pretty awesome. In case of even the small number of images data have used, and but everything is working fine. So this tutorial is all about how you can create 3D brain tumor segmentation and classification model in couple of minutes. What